My name is Shyam Prasad. I am the program manager of ASAP. So we are here for online class on mechanical engineering on the subject advanced mechanics of solids. So we have with us here 𝐿𝐵𝐽𝐸𝐸𝐿 ma'am. She is the assistant professor of Department of Mechanical Engineering at LBS College of Engineering, Kasaragod. She has done her BTech in Mechanical Engineering from University of Kerala and MTech in Machine Designing from University of Kerala as well. So she has 8 years of experience in teaching in academic field. So I welcome Mrs. Reshmi J. Devan ma'am for this class.
Thank you, SF team, for that nice introduction. Thank you very much. And dear learners, welcome to the session of torsion of non-circular bars. Okay, so myself is Reshmi J. Devan. I am working as assistant professor in the Department of Mechanical Engineering, LBS College of Engineering, Kasaragod. Okay, so today's session will be all about torsion of non-circular bars. And basically, non-circular bars, that is torsion of non-circular bars, actually it is from the 5th module of your syllabus. You can see the syllabus over here. And torsion starts from actually the second part, that is torsion is the second chapter of 5th modules. And from there, it covers all 6th module, that is 6th module is all about torsion. So in this, we will cover today the second chapter from 5th module and the first chapter from 6th module. That is all about torsion of non-circular bars. So basically, what is torsion? Okay, so this term is not a new term for you because you are in the 4th semester of mechanical engineering. So in the 3rd semester itself, we had to learn or discuss the term torsion. Okay, so this term torsion is sometimes not for all, but for some few people, torsion is getting confused with bending. So what is basically the difference between torsion and bending as applied to elastic structures? Okay, so we know that we can apply moments in structures, right? Or somewhere, sometimes due to the action of some loads itself, moments gets acted on the structures. So we know that all the bodies will have basically 3 coordinates. That means in a rectangular coordinate system, if you take, they are x, y, and z. So basically, you can assume any coordinate as the axis of the system. That means the longitudinal axis of the system. For example, you consider one circular bar, which is shown over here. Okay, so it has all the 3 axes, and we can take any axis as its a longitudinal axis, or the axis which is along the length of the bar. Okay, so if you apply some moment about the longitudinal axis, so you can see here the longitudinal axis, and in this figure some torque is being applied about the longitudinal axis. Okay, some torque is being applied in the free end. You can see one of the end of this bar is fixed. On the other end, that is at the free end, you can see some moment, or you can see the direction, right? So moment is applied. So this kind of moment, that means the moment which is applied above the longitudinal axis, this is known as torque. The moment is known as torque or twisting moment. Okay. Now, what is bending then? Bending or bending moments are applied in the transverse directions to the longitudinal axis. So what is transverse direction here? The other axis, right? So suppose you are taking Z axis as the longitudinal axis, the other axis, they are the X and Y axis. If you are applying some moments about X or Y axis, the moment will try to bend the beam. Okay, so that is bending. Clear? Now, we are concerned about only torsion here in this particular session. So, torsion is the twisting moment, or torsion is the effect of the twisting moment which is applied along or about, not along, about the longitudinal axis of the structure. Okay, so the twisting moment is known as torque, and effect of the torque is known as torsion. Okay, now this torsion of circular bars. So circular sections and torsion of circular sections, you are familiar, very familiar in your third semester mechanics of solid subject. There you will learn what is torsion of circular bars, and you have derived the famous equation, that is torsion equation, that you can see in the screen, that is T by J is equal to, sorry, I'm not seeing the slide right now. Okay, T by J is equal to tau by R is equal to G theta by L. This is the famous torsion equation, where T is the twisting moment or applied torque, and J is the polar moment of inertia with respect to the axis, longitudinal axis. Tau is the shear stress produced due to the applied torque. R is the radius, G is the modulus of rigidity or shear modulus, theta is the angle of twist, and L is the length of the structure. So this equation is very familiar. So this equation is actually based on certain assumptions. Okay, so those assumptions are only valid for the circular bars, or we can tell we have derived this equation based on the assumptions which are valid for only the circular bars. So whenever the assumptions are not valid, this equation is not valid. That means this equation is valid only for the circular parts. Okay. So we know that whenever some twisting moment is applied, whenever some any external force or moment is applied, the body tries to resist it. So as a matter of resist, there will be some shear stresses produced, or generally some stresses produced, which are the internal forces per unit area. So since twisting or torsion is created here, the type of stresses produced in the body or type of internal stresses produced in the body will be of shear. Okay, so whenever shear force is generated, what is our aim? As an engineer, our aim is to calculate this shear stress, right? Why? What is the reason for calculating or finding out the shear stresses? Because we all are concerned about the safety of the system, right? The safety of the system means what? The system where this particular circular sections or circular bars or circular shafts are used. So where these kind of shafts are used, where you can find the applications of torsion or twisting of shafts. You can find its application wherever there is a transmission of power. Right, this transmission of power. Transmission of power means power will be generated or it will be produced at some point, and we have to use it some other point, right? So we have to transmit it. So for example, you know the car or automobile, any automobile, in the engine power is produced, we have to transmit it to the wheels, right? Then only the system will work. Okay, and in turbines, for example, wind turbines, the power will be produced at the wind turbine part, right? And we have to use it. If we have to use it, we have to get it at the generator part. So from the engine to the generator, who is transmitting this power? That is the job of our shafts. Okay, so how the shafts are transmitting the power? They are transmitting the power by means of torsion. Okay, because the shaft will always rotate. So during the rotation of the shaft, the torsion is produced, and by means of torsion, power is transmitted. You will be knowing the equation for power transmission, 2 pi nt by 60, right? Where T is the torsion. Okay, clear. So there is where we have to use shafts, okay, or bars, or we will commonly see the application of torsion. So in all those systems, we have to ensure that the system is safe. Okay, that means no failure should occur. So no failure should occur means whatever stresses produced, whatever deformation produced should be within the allowable limit. So how can we ensure that whether they are within the allowable limit or not? There we should calculate the shear stress or the deformation. Okay, so in the case of torsion, the deformation produced will be of angular, right? So the twist or angular deformation is represented by theta in this equation. So what is our job as an engineer? As an engineer, our job is we have to ensure that the system is safe. For that, we have to calculate the stresses produced in the system whenever torque is applied, as well as the twist theta. Okay, the twist theta in the produced in the system due to the torque. Okay, now this torsion of circular bars already you covered in your third semester, and some important things about this torsion of circular bars. You can see shear stresses will be produced due to torsion, and you can see the variation of shear stresses. In the leftmost figure, you can see the variation of shear stresses. The variation of shear stresses will be linear with respect to the distance from the center. That means at the center, the tau max or variation will be very minimum, and towards the outward direction, it is increasing. I mean, with respect to the R, shear stress is increasing. So this is all about circular bars. Okay, next slide, please. Okay, so this circular bars or the equation, torsion equation for circular bars are derived based on these assumptions. So what are the assumptions of circular bars? The material of the shaft is uniform throughout the length. We know that the twist along the shaft is uniform, and the shaft is circular cross section throughout the length. Okay, transverse sections of the shaft remain plane before and after the twist. Please note this third assumption. This is very, very important. Then, fourth assumption is shear stresses vary linearly with the distance from the central axis. Yes, we agree. All radii which are straight before twist remain plane after twist. So the third assumption and fifth assumption, they are of very important. They have so much importance. Why? Because whenever these assumptions are not valid, the entire thing will change. That means all these assumptions or the torsion equation which we have seen before is derived based on these assumptions. Okay, next slide, please. Okay, now if the section is non-circular, what will happen? That means you can see some section over here, some rectangular section, right? Or square section, sorry. So some square section. So what if the section is non-circular? Is the equation shown before is valid here? Obviously no. Why? Because in this section, that is in this square section, some of the assumptions mentioned above are not valid. So which are they? Which are the assumptions which are not valid? The assumption that transverse sections of the shaft remain plane before and after the twist does not hold good for circular shafts. That means, what is this plane sections? So here in the rectangular shaft, you can see the shaft, entire shaft can be divided into some grids. Okay, you can see the grids. So if you take the one line which starts from top to bottom, and you take it before twist and after twist, that means in the undeformed condition and deformed condition, are they same? No, they are not same. In the undeformed conditions, they are very straight. That means the plane sections before deformation or before twist, they are plane. Okay. And what happens to the transverse sections after the deformation? That means in the deformed condition, they are no longer plane. They are twisted, right? So this twisting is known as warping phenomenon. Okay, W-A-R-P-I-N-G, the warping phenomenon. So the non-circular bars, in the case of or in the torsion of non-circular bar, the third assumption we stated before is no longer valid. That means the transverse sections of the shaft no longer remain plane after the twist. Okay, they undergo some kind of distortion, and this distortion is known as warping. So what happens here? Since the third assumption is not valid, our equation we have just seen before is not valid in this case. So we have to go for some other equation. Some other equations means we have to see how we can calculate shear stresses and how we can calculate torque and how we can calculate the angle of twist or deformation. Okay. So that is the interest of this session. That is what we are going to do, or we are going to see in this session. Is we are going to see, or we are going to discuss some methods to find out the shear stresses or the deformations in the case of non-circular bars. Okay, so this is analysis of torsion of non-circular shafts. So already so many times I mentioned the assumptions, all of the assumptions we stated in the case of circular shafts are not valid here. So we have to state some new assumptions. New assumptions are we have taken the z-axis as the axis of twist. You can see the figure over here. The shaft over here, the shaft is having some general shape. It's not circular anyway, so some general shape, and it has got its z-axis, direction as its axis, and its geometry or cross section lies in the x and y coordinates, right? Okay, so that is the first thing. And second is warping is approximately same for every cross section along z-axis. Already we have defined warping. Warping is the distortion of the transverse sections, and transverse sections distortion warping is approximately same along the z-axis. That means you take some point in the z-axis, some distance from the origin, okay, along the length. You can see some warping over here. You change the distance. You move forward to some other distance along the length. There also the warping phenomena will be same. That is, warping is approximately same for every cross section along z-axis. So now we are going to the analysis of torsion of non-circular beams. Torsion of non-circular bars. So analysis means we have to find out the shear stress. Already we discussed that once we have the shear stresses, then only we can ensure that whether they are within the allowable limit or not, then only we can ensure the safety of the system, right? So we have to have some equations for calculating shear stresses in the case of non-circular shaft. So for the analysis of that, we have to consider certain things. So what I'm going to do is I'm going to apply some torsion or a twisting moment in the counterclockwise direction. So you just consider one point P here, and after the application of twisting or torsion, the point P has moved to some new point P dash. Okay. So basically, the P had some coordinates before deformation. The coordinates of the rectangular coordinates are x and y, and its radial position is r. That means P is at a distance r from the origin, and its angular position is theta. Okay, it is making some angle theta with the x-axis. Now, what about this P dash? P dash has got new coordinates, right? X, y has been changed. Its r is same. R is almost same, you can tell. Then its theta, obviously it has changed, right? It has got some more theta, right? Theta plus some angle. So what is the theta plus angle? So you can see the angle between P and P dash. It is beta. So beta is the angular twist happen to point P due to the applied torque. I repeat, beta is the angular twist happen to the point P due to the torque applied. Okay, clear? Now what we have to do is we have to calculate shear stresses. So from where we can start, we have to get stress, right? So for getting stress, we want strain, right? If you have strain, you can calculate stress by applying Hooke's law. And if you want a strain, what you have to have? You have to have the displacements, right? So we will start from displacements. From displacements, we will go to strains, and from strains, we will go to stresses. So that is our aim. So we will start with displacements. So P has moved to P dash. So it has got some x direction movement and y direction movement, right? So what is its x direction movement? You can x direction movement means x direction displacement. You can represent the x direction displacement by u, right? So what is u? U is nothing other than the pp dash, the component of pp dash in x direction. How will you take pp dash first of all? From the geometry, you can write that P dash is R into beta, right? R is the radial distance, beta is the angle between P and P dash. So the distance P dash, the small arc, right? Small arc we can approximate to be linear because it is very, very small. So P dash can be written as R into beta. Now, what is P dash x displacement and y displacement, they are simply the sine and cos components. So u will be minus r beta sine theta and v will be r beta cos theta, right? Why the minus sign is coming? Because in the x direction, p has moved in the negative x direction. You can see we always take the right towards right, x is positive, right? And towards up, y is positive. So here u displacement is negative and v displacement is positive. Now what I can write? I can write sine theta as r sine theta as y. You just take the triangle formed between P, O and X. From the triangle P, O and X, you can take sine theta and cos theta. You can substitute over here. So what you will get? You will get u as minus beta y and v as beta x. So similarly, not similarly, that is the angle of twist or displacement in terms of angular twist per unit length. So we are talking the angular twist per unit length, right? So the length is in the z direction. So if we take z as the total length, what will be the total angular twist for the point P? So that will be alpha, that is per unit length into the total length. So you can substitute in for beta, you can substitute alpha into z, where alpha is angle of twist per unit length multiplied by total length will give you the total angular twist. So now your uv and w, you can see they have become minus alpha y z, v is alpha x z, and what is w? W is the z direction displacement, right? What is z direction displacement? Z direction displacement means the displacement which is happening in the z direction. So we have just seen that in the z direction, the sections are getting warped or distorted. Okay, so W represents the z direction displacement, and this displacement is known as warping displacement. And warping is a phenomena which is completely dependent upon the cross section of the body. It has no dependency on the z, means length of the shaft considered. It will be completely dependent on x and y. That means it's geometry. So W, the displacement, we do not know W right now. We can write it as a function of x and y. So that is W is equal to W of x and y. So please go through U, V and W, because as the next procedure, what we are going to do is we are going to calculate what? The strains. So for calculating strains, what are the equations? The next slide, please. So we know that equations for strains, right? So equation epsilon x as linear stress, what is the equation? It is dou u by dou x. And you just, we have now just seen that the u is minus alpha y into z. There is no x term, right? That means u is not a function of x. So epsilon x's will be 0. Similarly, what is epsilon yy? Epsilon yy is dou v by dou y, right? Dou v. V is the y direction displacement. So you have just seen that v is alpha into xz. So there is no y term in v. So epsilon yy will be 0. Similarly, epsilon z is dou w by dou z, right? And w, the warping displacement, is completely dependent on x and y. It is not at all dependent on w. So epsilon z is also 0. Right? So all the linear stresses have become 0. Now what happens to the shear stresses? Sorry, strains, shear strains. Gamma xy. So what is gamma xy? You just see what is the equation for gamma xy? It is dou u by dou y plus dou v by dou x, right? So it will also become 0. Clear? Now what we have now? The remaining are there. The gamma yz and gamma zx exist. What is gamma yz? Gamma yz is dou v by dou z plus dou w by dou y. Okay, so dou w by dou y, right now we do not know w value, so we will just write as dou w by dou y. And what is dou v by dou z? It is alpha x, right? So gamma yz is dou w by dou y plus alpha x. Similarly, what is gamma zx? Gamma zx is dou w by dou z, right? Plus dou u by, sorry, dou w by dou x plus dou u by dou z. So simply you can write. These are very elementary things. Okay. So we got now gamma YZ and gamma ZX. All other stresses are 0. So our aim is what? Our aim is to find out, all other strains as well. Our aim is what? Our aim is to find out stresses. Now you can write stresses because we know Hooke's law connects them, right? Hooke's law connects stress and strain. So you can simply write sigma x is 0, sigma y by 0, sigma z is at 0 because all the linear strains are 0. Similarly, tau xy is 0 because gamma xy is 0. So what is remaining? The remaining stresses are tau yz and tau zx. So what are they? They can be written as the modulus of rigidity into the shear stress, right? So tau yz will be equal to G into gamma yz and tau zx will be equal to G into tau zx. So you got the equations for tau z and tau xz. But my question is, are you able to solve any problems of non-circular shafts using these equations? We are not able to solve any of the non-circular problems just by using these equations of stress. Because we do not know W, right? We do not know, yes, you coordinates you can write, but we do not know what is this warping, how much amount of warping has occurred. So we have to change these equations to some solvable form. Okay, we got two equations. So two unknowns are there. So we have to go for minimum 2 number of equations for solving them, right? So what we can do? We can relate the stress terms. Now we got two stress terms, right? These stress terms with our already existing equations which contain stresses. I repeat, for solving these terms, that is tau yz and tau zx, what we can do is we can go back to our equations from elasticity, and using the equations of elasticity, we can solve these equations of tau yz and tau zx. And which equations of elasticity will help us to solve them? So we have got so many equations from elasticity throughout your first module and second module. You have so many equations which connect stresses and strains, right? So from those equations, which equations we can adopt now? We can adopt two equations. They are the equilibrium equations and the boundary conditions. I repeat, the equilibrium equations and boundary conditions. So using the equilibrium equations and boundary conditions, you can solve stresses. Okay, next slide.
Ma'am, we have one question.
Okay.
Ma'am, we have one question on non-circular body torsion. Can you please explain the first slide on non-circular body torsion? Ajit, VP, another student at KTU.
Non-circular, the first slide means non-circular, right?
Yes.
Next,
can you please explain the slide on non-circular body torsion?
Okay. So this actually represent a square shaft in torsion. Okay. So non-circular, its square is obviously non-circular, right? So whenever non-circular bar undergo torsion, we cannot use the already existing equations of circular bars for solving it, right? So we have to generate new equations. So for that, we have to first analyze them, right? We have to first analyze the phenomena of torsion in non-circular bars. So you can see two figures right here. First figure is the undeformed body, that means undeformed square shaft, and second is deformed square shaft. Okay, so what happens here? What happens is, I already mentioned that you have got so many assumptions in circular bar. One of the assumptions was the plane sections remain plane before and after the twist. So what is meant by this transverse sections plane? Sorry, transverse sections plane before and after twist. So what is this transverse section? Transverse section means the section which is transverse to the longitudinal axis. Okay, so you can take all the vertical lines over here. So the vertical lines represent sections, right? Because we have made it to small grids. So all the vertical lines representing the grids are transverse sections. So in the case of circular bars, before and after twist, you cannot feel any difference. How was the section, the transverse section before twist? It will be exactly same as after twist. But here you can see the difference. The sections, the vertical lines you can take. The vertical lines, they are no longer straight after the twisting phenomenon. Okay, so this twisting is known as warping in the case of non-circular parts. I think I just explained your doubt.
Thank you, ma'am. We can proceed to the next section.
Okay. Okay. Now we were talking about how to solve the shear stresses, right? We want to have the shear stresses in numerical values. So there you can use the already existing equations from elasticity. So they are equations of equilibrium and boundary conditions. So first we will see what are the equations of equilibrium. So these equations may be very familiar to you. They just represent the equilibrium condition in all three directions. So the first equilibrium equation here, this represents the equilibrium of forces in x direction. Second condition represent equilibrium of forces in y direction, and third equation represent equilibrium of forces in z direction. Okay, so now what we will do is we will just apply whatever stresses we have to these equations. Okay, let me take the first equation. So the first equation is dou by dou x of sigma x, right? Okay, we do not have any sigma x, so the first term gets cancelled. Second term tau xy, we do not have tau xy here, so second term cancelled. And tau xz, what is tau xz? Tau xz exists, but the thing is here we have to differentiate it with respect to z. But tau xz doesn't contain any z term, so that also will get cancelled. So the first entire equation gets cancelled. Go to the second equation. Second equation starts with dou by dou x of tau yx. We do not have tau yx over here, so first term is cancelled. We do not have sigma y over here, second term is cancelled. And third term, yes, we have tau yz, but there is no z term in tau yz, so we cannot partial differentiate with respect to z, so it will get cancelled. So what is remaining is the third equation, and in that only two parts, because sigma z we do not have. So in the third equation, third term get cancelled, and first term and second term exist. So we got an equation of equilibrium for torsion of non-circular shafts, and it is dou by dou x of tau zx plus dou by dou y of tau zy is equal to 0. The equation in the red color. Okay, so we have this equation. We can use this equation along with some other condition for solving tau zx and tau zy. Okay, next slide please. Okay, now we have two unknowns, right? Two shear stresses are unknown. So minimum we need one more equation. So that we can adopt from our existing boundary conditions. So what is boundary conditions? Conditions which exist at the boundary, right? So we have here two boundaries. In the figure you can see one is S, other one is R. S is the lateral side of the shaft, that is one boundary, and other one is R, which represents the contour, right? I mean geometry, that is the R region. Okay, so we have two boundaries. So we will first take the lateral side S, and we will try to write the boundary conditions. So what are the boundary conditions? Boundary conditions means since it is a surface, we can take the surface forces, right? So which are the equations which connect surface forces with shear stresses, generally stresses, surface forces with stresses. It is Cauchy stress equation. So the three equations you see in the screen right now is Cauchy stress equation, which relate the Tnx, Tny, Tnz. What is Tnx, Tny, Tnz? They are the surface forces, right? Tnx is the surface force which acts in a plane with normal n in the x direction. I repeat, Tnx is the force, surface force or any force which acts in a plane with a normal n and in the direction x. Similarly, Tny is a force in the plane which have a normal n and in the y direction, and TNZ is the force in a plane which is having a normal n and in z direction. Okay, so these equations are not new to you. They are very, very familiar. Tnx is sigma x nx plus tau yx ny plus tau zx nz. What are these nx, ny, nz? They are just direction cosines. And what will happen to these three equations? You just substitute your shear stresses. Okay, sigma x we do not have, tau yz we do not have, sorry, tau yx we do not have. The third term we have, but the thing is we do not have any nz here. What is nz? Nz is the direction cosine in the z direction. How will you calculate the direction cosines? Direction cosines represent the proportion of your normal n to the directions. Directions means x, y, and z. That means if you have a normal to the plane considered, how much it is represented in x direction, how much it is represented in y direction, how much it is represented in z direction. Normally, you can take nx as the cos of the theta between normal and your x direction. Ny is cos of the theta between normal and y direction. Similarly, cos of the theta between normal and z direction is nz. So here the normal with z direction angle will be 90 because z is our longitudinal axis. It will be perpendicular to the geometry. So cos 90 is 0. So we do not have any nz over here, but we do have nx and ny. You can just see the equations for nx and ny. In the figure, it is dy by ds or it is dy by dx and dx by ds. Okay, you can see the equations. Anyway, in our third equation, that is TNZ, TNx, what happens? In the first equation, third term, TNx, what happened? What happened is, first two terms get cancelled because we do not have any stresses. The third term of the first equation gets cancelled because n is 0. So similarly, what happens to the third equation? Second equation. Second equation is TNY, right? So you just substitute stresses one by one. You do not have any tau xy, 0. You do not have any sigma y. So that is also 0. You do have zy, tau zy, but nz is 0. So the second equation is also 0. What happens to the third equation? Tau zx is 0. Then sorry, not tau zx is not 0, it exists. Tau zy is not 0, the term also exists, but the third term, that is sigma z, is 0. So the third term vanishes. So we will have now our boundary condition. We have only one boundary condition for the problem concerned. So the problem is non-circular shaft torsion. For torsion of non-circular shaft, we have only one boundary condition or equation. One equation for boundary condition, that is tau zx nx plus tau zy ny is equal to 0. Okay. So now we got two equations and two unknowns. You can solve any problem. Okay. Any problem in the sense, any stress means tau zx and tau zy you can easily solve. Okay. Now go to the next slide, please. Okay, now we are concerned with the failure or the safety of the system, not failure, the safety of the system, right? For safety of the system, we have to ensure that whether the shear stresses are within the limit and also the deformation, right? Deformation means that angular twist. So our angular twist should be safe. So how can we calculate twist? So twist or angular deformation is actually created by whom? It is created by the applied torque, right? Always the external agencies will create deformation, right? So if you know the applied torque, you can calculate the deformation. So next is how we can have an expression for calculating the torque. Okay. So there you have to take the boundary conditions in the region R. Okay, region R. That is the cross section. That is the cross section. Okay, so in the region R, you can see that. Okay, generally what we do is we will take the forces and moments, and we will resolve them along x, y, and z, and we will see whether they exist or not. Since we do not have any forces applied. Yes. So px means x direction force, py means y direction force, pz means z direction force. They all are 0. Now coming to the moment part, mx and my. Already we discussed that mx and my, they are actually concerned with bending, and we are now talking about only torsion. So
okay, so we were talking about the boundary conditions boundary conditions from the lateral side. Boundary conditions on the lateral side, we got our first equation for solving shear stresses. Now we want one more equation. So for that second equation, we got from the region. From the region, we are going to take the equation for, or going to derive the equation for torsion, because after getting shear stresses, next is about deformation, right? We have to make sure that whether deformation also within the safe limit. So the deformation means angular twist here. So angular twist is created due to whom? Created due to the applied torque. Okay, so angular twist is created due to the applied torque T. So if we can have an equation or some relation for torque T, we can get some expression for theta. So next we are trying to develop an equation for torque. So you can see here, if the equations, they are the boundary conditions from the second surface, means the region R, okay, the R surface. So there we know that we have no forces, we only have one moment, and that is MZ. All the forces are 0 because we are concerned about torsion. Torsion is due to the twisting moment. So Px, that is the force along x direction, is 0, Py is 0, Pz is 0, and about the moments, Mx and My are 0. Why? Because Mx and My are the reasons, or they are concerned with a bending, right? Now we are concerned with torsion, so only Mz exists. And what is Mz? Mz is actually the moment, twisting moment, that is equal to T itself. T is the twisting moment, right, or torque. Now, how can we get an expression for MZ or T? This is here we have to use our elementary things. Our elementary thing is whatever force or external agency is trying to create some force, the material will try to, or the body will try to resist by creating stresses. So here twisting moment is applied to the body will resist the twisting moment by creating what? By creating shear stresses. So what you can do? You can equate the moments due to the shear stresses to the applied torque. Okay, moments due to shear stresses. So for moment due to shear stresses, you have to know the shear force, right? So how can we get the shear force? Just multiply the shear stress with area, right? Since we are talking about a very small region, we have to take the very small area dx dy. We will multiply it with shear stress. Then we will get shear force. Then you have to integrate it over for getting the entire thing. Okay, anyway. Now we are talking about moments of shear forces, right? Now what is moment? We are talking about shear stresses at the boundary. So you have to consider some region near the boundary. Okay, the shear stresses tau xz and tau yz, they are acting at the boundary, near the boundary. Okay, so they are at a distance x and y from the boundary, from the origin, right? So what are their moment distances or perpendicular moment arms? They are x and y. You have to take the corresponding moment arm and multiply it with shear force. Then you will get the total moment due to shear forces. This should be equated with torque. Then you will get the equation for torque. So the equation for torque is double integral over the region, because we have to get the torque for entire region, right? So we have to integrate, area integration. Then x into T and y. There the T and y term represent the shear stress at that particular boundary, the boundary concerned. Okay, into its moment distance, it is x. You know that TNY means it will act in the y direction. You just see it will act in the y direction. So a force or a force which is acting in the y direction, it will be at an x distance from the origin. So the momentum will be x. Similarly, TNX is acting in the x direction. So the momentum from the origin will be the distance y. Correct. So this is the equation for torque. So now what are where are we? We got the equations of shear stresses. We got the equation of torque. Equation of shear stresses means we just got two equations. And now we can solve them. Okay, because two equations, two unknowns we can solve. Okay, now we got one more equation for torque. Next slide, please. Okay.
Ma'am, we have 10 more minutes.
Okay. Now we can use two approaches for torsion analysis. Now we got equations. Now we have to solve them, right? Then only we can get tau xz and tau yz. So for the solution of these equations, we can use two approaches mainly. The approaches are known as, first approach is St-Venant's semi-inverse method or St-Venant's method, and second method is Prandtl's method. Okay. So we will see one by one. So what is St-Venant method? St-Venant actually thrusted, or he put his entire consideration to the warping. Okay, so we already have seen warping is the W displacement and it is a function of x and y. So what he did is he introduced some phenomena known as some function known as warping function psi. Okay, so what is psi? Psi is warping function. And why? How psi and W are connected? They are connected. W is equal to alpha. Alpha is the twist, right? Angular twist into the function psi. So what he did is he considered warping and he introduced some function known as warping function, and he related the warping displacement W to the function, that is W is equal to alpha into psi of xy. So you know warping is entirely dependent upon x and y. So function is psi of some function in x and y. Okay, now on the other method, what Prandtl did, Prandtl actually followed the St-Venant's approach only, but he made some changes. The main change is instead of using warping function psi, he used the already existing stress function. We know what is stress function, right? In our third module and third module, we have used stress function phi. Okay, so stress function phi and shear stresses can be, all the stresses can be connected. Okay, because that is why they are known as stress function. They connect stress, right? Stress. Okay, so that is Prandtl's method. So Prandtl introduced stress function. St-Venant introduced what? Warping function. Now, how we can use all this? So going back to St-Venant method. So what St-Venant method tells is we can write W in terms of psi. So what will our shear stresses become? Shear stresses are tau yz and tau xz. Now you can see the equations for tau yz and tau z, tau xzx in terms of psi. So they are G into alpha dou psi by dou y, because for W we substituted alpha into function psi. Similarly, tau zx, G into alpha into dou psi by dou x minus alpha y. So instead of W, you should give alpha into psi of xy. Okay, so this is St-Venant's method, and using St-Venant's method, now we got shear stresses. Now, what is Prandtl's method? Prandtl's method is very easy, because tau zx we can write dou phi by dou y, and tau yz we can write minus dou phi by dou x. This is basic from stress function. We know how to use stress function, but the thing is there you used stress function only for two-dimensional cases. Now we are here talking about the stresses in Z plane also. So there you can use stress function phi. So tau zx is dou phi by dou y, tau yz is minus dou phi by dou x. So using these relations, we can solve our torsion problems. Okay, now next slide, please. Okay, so first St-Venant method. Now we got shear stresses. What is our aim? Our aim is to solve for shear stresses, right? So now we got shear stresses. So we have our equilibrium equation as well. So next is you can substitute the shear stresses into the equilibrium equation. What is equilibrium equation? Dou by dou x of tau zx plus dou by dou zy of dou by dou y of tau zy is equal to 0. Instead of tau zx and tau zy, you just substitute in terms of psi. Okay. Now what you are going to get is g alpha into, that is alpha g alpha into dou square psi by dou x square plus dou square psi by dou y square is equal to 0. G theta can be taken to the other, g alpha can be taken to the other side. So what you are having now, del square of psi is equal to 0. Del square of psi is equal to 0. Okay, so we got an equation. We can make use of this equation somewhere to solve torsion problem. We will see that. Now going to Prandtl's method. What is Prandtl's method? Prandtl's method uses stress function. So I already told you Prandtl's method, actually Prandtl followed Saint-Venant. So now what we can do is we can make a comparison between the shear stresses using psi and using phi. Shear stresses using psi and using phi. So you can see the comparison in the screen. Tau yz and tau zx, they are written using psi and phi. So from the comparison, we will get the equation. If del square psi is equal to something, you can write del square phi is equal to something, right? But by comparison, we are getting dou square phi by dou x square plus dou square phi by dou y square is not 0 here, it is minus 2g alpha. So these two equations are known as the governing equations for torsion problem of non-circular shafts. So del square psi is equal to 0 represent the governing equation in Saint-Venant's method. Del square phi is equal to minus 2g alpha represent the governing equation of Prandtl's method. Next slide. Okay, now we have one more thing, torque transmitted, because we want to know theta as well, right? So we got the equation for torque transmitted from the previous previous slide we have seen. Now we are going to substitute instead of the equation, instead of Tnx and Tny, we are going to substitute the real terms. So what is Tny? Tny is the stress acting in y direction, right? In the Z plane. Z plane means the plane of geometry. So Z plane in y direction, that is tau yz. Similarly, what is Tnx in Z plane x direction, that is tau zx. So they are multiplied with their perpendicular momentums and into area, and they are integrated over the region R. So you can go for the integration, that is up to you. This just mathematical calculations. And now what we are going to do, we are substituting. This is Saint-Venant's method. So we are substituting tau yz and tau zx in terms of psi. Clear? So after substitution and proper integration, what we are having now, we are having, you cannot integrate fully here because we do not know the region, right? If we know the region only, we can just take the limits and properly integrate. So just you can write the integration sign over there. That's all. Once you are given with the type of the contour or type of the region, you can go for integration. There. Okay. Now what we have? We have the equation for T in terms of psi. Please note the equation. Please note the equation. Select the equation. T is in terms of G alpha x, y and psi. Psi is the warping function. So the entire integral term you can just represent by using a letter J. So T is equal to G into J into alpha, where J is the entire term inside the integral. So this is the equation for torque from Saint-Venant's method. Next slide, please. Now you are seeing the Prandtl's method. So in Prandtl's method, how to find out the torque transmitted? Same equation. Same equation means the double integral over R x Tny minus y Tnx dx dy. Instead of Tny, you can substitute tau yz. Instead of Tnx, you can substitute tau zx. Now here you have to substitute the shear stresses in terms of phi, the stress function, right? So you can substitute shear stresses in terms of phi. So do the integration part and all, that is up to you, because they are just mathematical things. And finally, what you are given with? You are given with 2 times double integration over phi. Okay, double integration over phi dx dy. That means if you know the stress function, you can integrate it double times, means for the area, and multiply it with 2, you will get torque. That is Prandtl's method. Okay, so now we have seen torque transmitted by Prandtl's method, torque transmitted by Ksane-Winant's method, and the governing equations for both Ksane-Winant method and Prandtl's method. Next slide, please. So these are some of the questions asked in previous university questions. You can just go through it. So in all of the questions, as a general, what you have to calculate is, you have to calculate shear stresses. You have to calculate, calculate in the sense, sometimes you have to calculate numerically, sometimes you have to just write down the equations. Anyway, you have to find out or calculate shear stresses or the twist. Okay. So now using Ksane-Winant method or using Prandtl's method. Next slide, please. Okay, these are the equations. Okay, next slide, please. Next slide. So these are some of the questions. Now, as per your syllabus, we have to go for the solution of only 2 sessions, cross sections, using Ksane-Winant or Prandtl, and they are elliptical cross section and circular cross section. Okay, so we will have some discussion on the elliptical cross section quickly. So this is the solution for elliptical cross section using Ksane-Winant method. So what was our Ksane-Winant method? Ksane-Winant introduced, or he introduced some warping function psi, which represents the z direction displacement w, right? So we do not know right now what the function is. It can take any form. Okay, we in your stress function approach for 2-dimensional cases, for plane stress and plane strain problem, you know how to establish a stress function, right? By so many trial and errors, actually you have to establish your stress function. But luckily we have some ready-made equations for stress functions, so we can use it. So in the similar way, here also we have some ready-made functions for elliptical or circular cross section. So for elliptical cross section, psi is AXY. Don't think that simply you can write some function and it can be the elliptical cross sections psi. By some trials and errors, somebody have proven that this is a function. So that is why we are using psi is equal to AXY, where A is a constant. We just have written that psi is equal to AXY. Now we have to see whether it represents the ellipse. Okay, whether it represents the ellipse. So first of all, you have to see whatever function you expressed, it should satisfy the governing equation. Okay, so what was our governing equation? Our governing equation was for Ksane-Winant method, it was del square of psi is equal to 0. So yes, here it satisfies because AXY. If you double 2 times, if you partial differentiate, the function will become del square of function will become 0. So the function satisfies governing equation. So first part is over. We introduced some function and we proved that yes, it satisfies. So next slide, please. It satisfies the governing equation. So next part is, we are telling that this function is for elliptical cross section, but we have to prove that whatever we told. We have to prove whatever we told. So next we have to see whether it is actually for elliptical or not. So how we can prove that? So elliptical is the boundary, right? Ellipse is the boundary, right? So from the boundary condition, you can prove that the expression or the function psi is equal to AXY represents ellipse. Okay, so we are taking the boundary condition. This was the boundary condition for our Ksane-Winant's method. Okay, so Ksane-Winant, you just take the general boundary condition. In the general boundary condition, you have W terms. Okay, so in the W term, you can substitute psi now you will get the boundary condition for Chern-Winand method. The first equation written over here represents the boundary condition for Chern-Winand method. It contains G alpha into dou psi by dou x minus y. That is the shear stress into its direction cosine dy by ds minus again G alpha into the shear stress dou psi by dou y plus x into its direction cosine should be equal to 0. Now you can do the proper mathematical calculation. That means dou psi by dou x you can do. Psi is axy, so dou psi by dou x you can do. Dou psi by dou y you can do. You can substitute. So finally, what you are getting? Finally, you are getting that 1 plus a into x square plus 1 minus a into y square is a constant. Yes, this is in the form of the equation of ellipse. So yes, whatever function we have chosen is representing an ellipse. So this is how you should prove that the function chosen, the warping function chosen represent the given geometry. Next, please. So this is in the form x square by a square plus y square by b square is equal to 1. So you can prove that this is for ellipse. Now from the comparison, you can just find out the constant a, then you can substitute the constant a. So psi will become b square minus a square by b square plus a square into xy. So it represents the warping function for elliptical cross sections with semi-axis a and b. Next slide, please. Now next we have to find out our torsion, right? Next job is we have to find out torsion. So you can just write torsion equation from Chern-Winand's method. What was our torsion? T is equal to G into J into alpha. What was J? J was some integral term, right? So that term is written over here. So it is in the term of psi. So what you have to do? You have to find dou psi by dou y, dou psi by dou x and substitute there. So you will get J. Right. So finally, after substitution and after seeing, we can see that a plus 1 into integral of y square dx dy plus 1 minus a into integral of y square dx dy we are getting. So from elementary mechanics, you have to see that double integral of y square dx dy is Iy, right? The polar moment of inertia in y direction. And what is double integral over y square dx dy? It is moment of inertia in x, that is Ix, right? So what is Iy and Ix for ellipse? It is pi aq by b by 4 and pi bq a by 4. Okay, so you can substitute it. So you will get G. Substituting the value of a as well. A you have to substitute, it is a constant. Now you will get capital A. Now you will get T is equal to G alpha into pi aq bq by a square by b square. Next slide, please. So this is torsion. And from torsion, I already told you, you can calculate alpha because torsion contains alpha. So you can write alpha is equal to something. Okay, next. So this is the important part. Shear stresses. So you have the equation for shear stresses in terms of psi. There you can substitute your psi now. You got your psi now in terms of semi-major axis A and B. Now you can take dou psi by dou y, dou psi by dou x. You can substitute for tau yz and tau zx. You can see what is tau yz? 2 into tx by pi a cube b. What is tau zx? 2 into ty by pi a b cube. So if you know the semi-major axis and for which point you have to calculate shear stresses. For example, I am telling you that for x is equal to 3 meter and y is equal to 5 meter, you just calculate shear stresses. Provided I have to give you the cross section and I have to tell you the cross sectional features, right? Then you can calculate tau yz, tau zx, torsion, twist, everything, and you can make sure, you can ensure that whether the given system or given whether shaft, non-circular shaft under torsion is safe or not. So this is how we proceed for analysis of torsion of shear stresses, torsion of non-circular shafts, and it's the okay, students. So now you are seeing the solution for circular cross section using Prandtl's method. So already we discussed about Chern-Winand's method, and we use Chern-Winand's method for solving an elliptical cross section. Now we will use Prandtl's method to solve. Can you make the slide full view? Now we can use Prandtl's method for solving the circular cross-section. So first of all, Prandtl's method is based on the stress function. Okay, stress function phi. So first of all, we have to get some function, right? So we have to establish some function. So in the method, what we do is, in Prandtl's method, what we do is, first of all, we write function phi from the contour's equation, right? So here the given contour is circle. So circle's equation is x square plus y square is equal to c square in xy coordinate. So what we do is, using this equation, we write phi. So we write phi as some constant m into x square plus y square minus c square. So whenever you write the phi, one thing you have to see that whatever phi you are writing, the phi should be 0 along the boundary. That means the boundary considered here, it is circle. So along the boundary, the phi should be 0. Now my phi is what? Some constant m into x square plus y square minus c square. So I know that x square plus y square is equal to c square, right? So the term is 0. M is a constant, so my phi is 0. So this is the one thing you have to see whether when you are using the Prandtl's method or whenever you are writing phi. Okay, next slide. Okay. Now we established our phi, that is stress function. Our aim is what? Our aim is to go for shear stresses and the torsion and twist, right? So first of all, we have to eliminate the constant m. So how can we eliminate the constant m? We can eliminate the constant m by taking our governing equation of Prandtl's method. So what was our governing equation for Prandtl's method? It was dou square phi by dou x square plus dou square phi by dou y square is equal to minus 2g alpha, right? So you just put the value of dou square phi and dou square phi by dou x square and dou square phi by dou y square, then you will get the value of m. Dou square phi by dou x square is 2m, dou square phi by dou y square is also 2m. So from it we are getting m as minus g alpha by 2. Alpha is the twist, right? Now you can substitute m for phi. Now you are getting phi is equal to minus g alpha by 2 into x square plus y square minus c square. Now everything is very, we have actually partially solved our problem because we got our phi. Now next thing is finding shear stresses. Shear stresses are what? According to Prandtl's method, shear stresses are tau zx is equal to dou phi by dou y and tau yz is equal to minus dou phi by dou x. So you just take dou phi by dou y and you just take dou phi by dou x. You are getting shear stresses. So if you are given with the coordinates and if you are given with the twist, you can calculate. Modulus of rigidity is a non-quantity, right? It's a material property. So we can calculate shear stresses. Now next is the torque transmitted. So torque transmitted, we already got the equation for Prandtl's method. It is 2 times integration of phi, right? So you just do the integration of phi. What is our phi over here? It is x square plus y square minus c square, right? And now to make integration comfortable, you know how to make it comfortable. We can give some substitutions. You can substitute x square plus y square as r square. So dx dy will become 2 pi r dy. So substitute, and then the double integration will become single integration. You can set the limits from 0 to r. Actually, I'm not going to somewhat deep into it because these things are already you have covered in your mathematics subject. I think the same equations you will study there for ellipse and circle, the area integration. Okay, so from the integration, we are getting torque as g alpha into pi d raised to 4 by 32. What is this pi d raised to 4 by 32? Somewhere we have heard it, right? It is actually the polar moment of inertia, right, of the circular shaft. So T is g into polar moment of inertia into alpha. So from here you can write your alpha. Alpha is equal to T by g into polar moment of inertia. So this solves our shear stresses and the angular twist using Prandtl's method for a circular cross sections. Next slide. So with this, I just conclude. Throughout the session, my reference was the textbook by L.S. Srinath, Advanced Mechanics of Solids by L.S. Srinath. So this is one of your textbook prescribed in your syllabus. Okay.
So with this, our session came to an end. So we had with us Rashmi ma'am from LBS College Kasaragod. So we went through portions on advanced mechanics of solids, and Rashmi ma'am has taken us through torsion of circular portions, which covers torsion of circular bars, non-circular bars, and she has discussed with us the